Hello students, welcome to the lecture of Basic Concepts of Chemistry. In the last lecture, we have discussed about the law of conservation of mass, which stated that mass can neither be created nor be destroyed, it can be converted from one form to another. It is similar to the law of conservation of energy, and we have already explained this law and we have practiced some numerical problems. So, today we will solve one more numerical problem based on this law, and then we will study its limitations and we will move on to the next laws. Okay. So, let's start. So, the question is, sodium chloride NaCl can be formed by the reaction of sodium metal with chlorine gas. What is chlorine gas? Chlorine gas is Cl2. Okay. If 45.98 grams of sodium combine with an excess of chlorine to form 116.89 grams of sodium chloride, how much chlorine gas is used in the reaction? Okay. So, sodium chloride can be formed by the reaction of sodium metal and chlorine gas, right? So, the weight of sodium is given, weight of sodium chloride is given. We will have to find out the weight of chlorine that is required. So, first let's write the reaction. Sodium plus chlorine gives sodium chloride. We will have to balance the reactions. Okay. So, if there are two chlorines, then we will put 2 here. So, we need 2 sodium. So, this is the reaction of the formation of sodium chloride from sodium and chlorine gas. Okay. So, by the law of conservation of mass, mass of reactants should be equal to the mass of products, right? So, what is the mass of reactant? Mass of reactants is mass of sodium plus mass of chlorine, right? This is equal to that mass of products, that is the mass of sodium chloride. Okay. So, we know the mass of sodium. What is the mass of sodium? This 45.98 grams. So, 45.98 grams plus, we don't know the mass of chlorine, that we need to find out. So, we will consider this as X equals to the mass of sodium chloride, which is given as 116.89 grams. So the mass of chlorine, that is X, will be equal to mass of sodium chloride minus the mass of sodium. So 116.89 grams minus 45.98 grams, which is equal to 70.91 grams. So this is the mass of chlorine in this reaction. Okay. So we had already solved this numerical in the last lecture, and today we have solved this one. Now we will discuss about the limitation of the law of conservation of mass. Limitation of law of conservation of mass. Okay. So, like any other law, law of conservation of mass also has some limitation. Although this law is applicable for most reactions, but this law will not be applicable when a high amount of heat or energy is absorbed or evolved in a reaction. Okay. So, the statement is, the law of conservation of mass fails for those chemical reactions in which a large amount of heat is evolved or absorbed during the reaction. Okay. So, we know that we have two laws, the law of conservation of mass and the law of conservation of energy. Okay. We have already discussed the similarities of these two laws. So, sometimes it happens that mass and energy are interconvertible. Like by the equation of Einstein, E is equal to delta mc square. So, this delta m is the difference in mass or the change in mass. So, by Einstein's equation, it is possible to correlate mass with energy. So, mass to energy or conversion or vice versa is also possible. Such things are seen for reactions like the nuclear reactions, where a large amount of heat or energy is evolved. There are some reactions where a large amount of heat is absorbed also. So, for such reactions, the mass of the reactants are not always equal to the mass of the products. Okay. So, we know that for nuclear reactions, we start with a heavier nuclei, and due to nuclear decay, we get a lighter nuclei. So, in that case, the mass of the reactant is not same as the mass of the product. So, their conservation of mass fails. So, this is the limitation of law of conservation of mass. Okay. So, this can be, the example for this limitation can be nuclear reactions. Okay. So we have completed the law of conservation of mass. Now we will start another law which is known as the law of definite proportions or constant proportions. Law of definite or constant proportions. Okay. This is also known as the law of definite or constant composition. Okay. So these are the same laws. Law of definite proportions. This law was proposed by Joseph Proust in 1797. Okay. So we will see what is the statement of this law. Okay. So this law stated that a given compound always contains exactly the same proportions of elements by weight. Okay. So this law of definite proportion states that a given compound always contains exactly the same proportions of elements by weight. Now, in chemistry, there are various methods of preparing a single chemical compound. Okay. We can collect from nature, we can synthesize in lab, and also there are various methods of synthesis. But for a certain compound, the components of this compound or the elements that have formed this compound will always remain in a definite proportion no matter the method of formation of that compound. Okay. For example, let's say water. Okay. We can collect water from the tap. We can collect water from river or ocean. We can also form water as a product of some chemical reaction. But no matter how this water was formed, water will always have the formula of H2O, and the ratio of hydrogen to oxygen will always be 2:1. So this is the law of definite proportion. This law can be expressed in terms of proportion as well as in terms of percentage. Okay. In fact, Joseph Proust has at first described it in terms of percentage. So we will see how it was proposed. So he worked with 2 samples of cupric carbonate. Okay. So we will discuss about Proust's experiment. Okay. So what happened? He worked with 2 samples of cupric carbonate. What is cupric? Now copper can have commonly two oxidation states, that is Cu1 or we can say Cu plus and Cu2 or Cu2 plus. So this one is known as cuprous and this one is known as cupric. Okay, so cupric carbonate is basically copper 2 carbonate. So this has a formula of CuCO3. Now this has copper, carbon and oxygen. Okay. So Proust measured the percentage of each element in the two samples. Okay. So the two samples that he had collected was natural and synthetic. So he made a table, percentage of copper, percentage of carbon and percentage of oxygen, and he analyzed these two samples, natural and synthetic. So the natural sample had 51.35% copper, 9.74% carbon and 38.91% oxygen. Now when he measured the composition of the synthetic sample, he got these exact same results. Okay, 51.35% of copper, 9.74% of carbon and 38.91% of oxygen. So the two sets had exactly similar composition of the elements. So from this it was concluded that no matter the starting point or no matter the source of the compound will always have the definite ratio of its constituent atoms. Okay. So let's see some examples. Okay. Let's consider CO2. So CO2 can have many methods of formation. One method can be exhalation. Another method can be combustion of hydrocarbons. Okay, there can be other methods too. Now we will see the ratio of the masses. So carbon plus 2 oxygen, this is carbon dioxide, right? So carbon has a mass of 12. So there is 1 carbon in carbon dioxide, so 12 into 1 we get 12, and the mass of oxygen is 16. We have 2 oxygens here, so it is 16 into 2, that is 32. Okay, so the ratio of masses can be this can be written as 3:8 if we divide them by 4 on both sides. Okay. So this is the simple ratio. Now, doesn't matter what is the source of carbon dioxide, the ratio will be always the same. Now, if we calculate percentage of carbon, so 12 divided by 12 plus 16 into 2, that is 32. This is the total mass of carbon dioxide and this is the mass of carbon. So, if we calculate the percentage, it comes as 27.27%, and percentage of oxygen will be 32 divided by 12 plus 32 into 100, which comes as 72.72%. Okay. Or we can say this is 27%, this is 73%. So this is the percentage composition of carbon dioxide. We will discuss further about the law of definite proportions in the next lecture. Thank you.